This is CTS560 online, Computational Molecular Science, and I'm Professor Zygmunt. What I'd like to do now, assuming that you've already set up an input file using the GaussView program and have now logged out of the N0 machine, you're back in your main machine, I would like to show how to run the kind of calculation that we will often do using the Gaussian program and visualize the results using GaussView. So the first thing is that once you log out of the N0 machine and you're back in your home machine, unless you were already in the specific directory that contained your input file, you have to go to that. So for me, I have to type cd for change directory, cd CTS560, and then when I look at that, I type my ls-l command. I have a directory O2, so I type cd O2, and of course there I have the original input file with the tilde and the one that I edited and named o2_uff.com. If for some reason before I run the calculation I would once again like to view that file, perhaps to edit it, I can use the gedit command, if I can spell it correctly, o2_uff.com, and when I do that, the window pops up and I can scroll through that with the cursor and look for anything that I might want to change. So this looks good, in which case without any changes I will just close the file, and now the program, which you will always run on your main node, your main machine, not on the N0 machine, is run by typing GO3, which stands for Gaussian 03. And that's the program that will take the geometry of the molecule in this input file and in this case will optimize the geometry to reach the lowest energy configuration, the lowest energy structure. But I have to tell Gaussian which input file to use, so I use the left caret and then the name of the input file and a space, and then I use the right caret and give the name of an output file. And by default, Gaussian is looking for output files that have the suffix .log. And so I always use the same name as the input file except with the suffix .log. And once again, I want to run this calculation in the background so that I can continue to use the terminal, perhaps to look at files while the calculation is running. So before I hit return, just note what this does. This calls the program GO3 and tells it to use the input file. The left caret means that the next string is an input file. The right caret then directs the output to the log file. The ampersand puts it in the background, and I will hit return. And then the process ID number is displayed, which is 9100. Now I can type ls-l while the calculation is running, and I'll see two new files that appear. One is the log file, which contains in text format the output information, and the other is the checkpoint file. I specified this name in the input file. This is a binary file, and we will sometimes use it, but we will never look at it directly because it's just strings of ones and zeros. So the log file is the one that we will most often view. And lo and behold, in just a few seconds the calculation has finished. And if I'm still logged in, when the calculation finishes, I will get this message that tells me it's done. So there are two ways of looking at the output results. One is to look at the file directly using the more command from Unix, so o2_uff.log. I can more the file. What more does is it displays the file one screen at a time, and I advance through the file one line by hitting the enter key like that, or one page at a time by hitting the space bar, which scrolls through it. And there is a very nice discussion in chapter 17 of your textbook that walks through the output of a typical Gaussian calculation. So I won't do that right here, other than to show, as I page through it, that the initial information about the structure of the molecule is displayed here. You can see the title line and then the charge and this multiplicity that tells me it's a triplet calculation. The original bond distance of 1.25 angstroms is displayed. And then there's many additional screens of information that are somewhat complicated, but what the program is trying to do is to find the coordinates of the atoms in the molecule that will give the molecule its lowest possible energy, because we asked it to do a geometry optimization. And so it will calculate the forces that the atoms experience, and here's the important part of the calculation. It applies a test when it calculates the forces as to whether or not the forces and then displacements of the atoms are below a certain threshold, which will tell the program that the calculation is optimized. And in this case, all four of these tests are met because the yes word is displayed in answer to the convergence test. And so it says optimization completed, stationary point found, which means it has found a stable structure for this molecule. So now if we go a little bit further down, we will see some additional information. It tells us the final structure in terms of the initial Z matrix, which is the program's name for the input file, and it tells us the new bond length, which is now the bond length at which the energy of this molecule is a minimum. And so instead of the 1.25 that we submitted, we get 1.1944, and then there's some additional information in the very end of the file. And one of the things that's in here that's important, HF is the symbol that precedes the energy of this structure. And the energy of O2, using this method of calculation, actually turns out to be 0, because the energy is being given relative to an ideal state of this system. And so the O2 molecule has an energy on this scale of 0 Hartrees. Now that by itself doesn't really mean anything. What we will sometimes use these energies to do, though, is to assess the relative stability of two particular configurations of a molecule. In the case of O2, it's not very interesting because there really aren't any other configurations of diatomic oxygen that we can come up with. Just one where the two atoms are separated by a certain distance. But in much more complicated molecules, and the second part of the assignment this week deals with ethane, there are more than one types of configurations that the atoms can be in. And so the energy that's reported here for different configurations will allow us to test to see which configuration, which geometrical structure is actually the most stable. And that's what's important here. We asked not only for an optimization of the geometry, but also for a frequency calculation. And here we see that there's a normal termination of Gaussian O3, and now it goes to calculate the frequency. And so if I page through the remaining parts of the output file, one of the important pieces of information here will be the vibrational frequency. And here we can see that the vibrational frequency in units of inverse wave numbers, centimeters to the -1, you can see harmonic frequency, centimeters to the -1, the vibrational frequency of this oxygen molecule is 1743 inverse centimeters, which is not as good, not in as good an agreement as the value that you found in last week's assignment, because this molecular mechanics method is much more approximate. In any case, there's more information in this file, but I won't try to summarize it here. What I want to do next, though, is allow you to visualize the output using the GaussView program. And to do that, once the calculation is finished, in order to run GaussView, we again use the SSH -y N0, which takes us to the N0 machine, and then we can type GV ampersand in order to open up the GaussView program. All right? And in this case, what I want to do is close this initial blue window because I'm going to open the output file. Now, having gone to N0, I have to now navigate to the directory that has the files you can see now I have lots of directories. So the CTS560 directory, I double click on this with the left click, and then I double click on the O2 directory, and what it's looking for is different file types. But what I want to do is change this so that it looks for Gaussian output files which have the format star.log. And now you'll see that that file is listed. And before I open it, I also want to always click Read Intermediate Geometries. So I double click on it, and now a window opens with the final geometrical structure of my system. Again, it looks odd because initially it looks like there's just a single atom, but if I left click on the mouse and rotate the structure, I can see that I've actually got a diatomic oxygen molecule. And once again, if I go to the question mark icon, which is the Inquire button, and click on that, and then click back to my graphical display window, if I click the two atoms in succession, and that's using the left mouse button, I get the bond distance, which just happens to be the same distance reported in the output file. So that's the equilibrium distance that this method uses, or this method obtains when it does the geometry optimization. Now, one more thing I can show is an animation of the vibrational frequency. For a frequency calculation, if I go to Results and I click Vibrations, then for more complicated molecules, there will be a list of all of the different vibrational frequencies for all of the different types of vibrations the molecule can have. But in this case, the simplest of molecules, a diatomic system, there's only one frequency. There's only one vibrational pattern. And so if I click Start, then I'll see in the window the atoms will move back and forth, not in real time, of course. This is simply an animation, but it shows the pattern of the vibration at this particular frequency. And depending on your internet connection, this may happen very quickly or very slowly, but if I click and drag the frames per cycle to a little larger value, and then drag the displacement slider bar down to a smaller value, then we'll get something that's a little bit more manageable to display. And you can see that the graphics leave a little bit to be desired, partially because of the internet connection. But in this case, I can still rotate the structure as the vibrations are occurring in case I want to get more information about just what exactly is going on. And so this can be very useful when we're using our calculations to understand vibrational frequencies, and when we're comparing our results to perhaps a vibrational spectrum that's obtained experimentally. We might be able to look at a particular feature in the experimental spectrum and compare it to the calculated spectrum and figure out just what that peak on the infrared vibrational spectrum corresponds to in the real molecule. When I'm done, I'll stop and cancel, and then of course when I'm finished again, I'll close this out, close out of GaussView, and I'm finished then on N0, so I will exit it, and assuming that I'm all done completely, I will exit the machine, and then the actions will be log out. As usual, yes, I'm sure I want to log out, and after just a moment, I will be returned to the Connect screen. I can close down the entire program, and then I return to my Windows desktop. So I hope this is helpful as you begin to use GaussView and Gaussian to set up molecular calculations.